Good afternoon, everybody. My name's Carl Meyer from GÉANT, and I'm here to introduce Bruno de Troch from Nokia, who is going to be talking to us about 1.6 terabit Ethernet, which is quite an extraordinary capacity, and how that'll be used within our environment, within our services. And without further ado, I shall pass over to Bruno. Thank you, Bruno.
Okay, thanks a lot, Carl, for having me here to talk about 1.6 terabit Ethernet. So for people who don't know me, I'm working for Nokia in the network infrastructure organization. So we are building products for the IP, optical, and fixed access markets. And for the topic of today, of course, it's touching a bit on, or mostly on the optical side and on the IP side. Right. And as Carl said, I think it's easier if we just keep the questions till the end. I have roughly, I think, 35, 40, 45 minutes worth of content. And then, so I'll go through this. And then after that, we'll check, or I'll check your questions and then see which ones I can answer. So first question you may ask is, okay, why now, right? So why terabit Ethernet in many networks are there today? We see 400 gig only being deployed right now, maybe some 800 gig starting to be seen in networks. So it seems a bit early for 1.6, but I thought, okay, it's maybe a good timing to give you an idea on where we are going with standardization. Are we almost ready? When can we expect equipment and so on? And so that is the reason that we organized this webinar, right? So let me try to fix this. Yeah, okay. So let me see if this works, and I can move to the next slide. Okay. So why 1.6 tera, right? And easy answer could just be, well, this is the next Ethernet speed, right? So we've had a long history of Ethernet, and I'll come to that in a minute. And so for some people, for some customers even, it looks like, okay, now this new thing is available, I will have to jump. And so they followed us with 100 gig, 400 gig, 800 gig. Now once 1.6 will become available, they will also deploy 1.6, right? It's just the next speed around, right? So that would be kind of the easy answer, but probably not the most, from a commercial point of view, financial point of view, the right driver, right? So what we really see as drivers today for this type of speeds for 1.6 tera is what's happening in data centers, and more specifically into AI data centers. And I will again go a bit deeper in that perspective on why that is happening, how these data centers are being built, and why you have a benefit if you can do 1.6 tera instead of the previous speeds that we had in Ethernet. And then the second reason is, of course, these data centers need to be interconnected. We need to get access to these data centers, so there is more traffic going into the data centers and between the data centers, and as a consequence, of course, there is also going to be more traffic on the wide area network, and these will then lead to higher capacities being needed there as well. So I'll dive a bit deeper into all of or kind of these two use cases, but in general, I think if I should summarize, it is of course this exponential growth that we're seeing in the network that we were actually already seeing before, with impact of cloud generically, but then also gaming and video, that is now being even more extended with AI and the consequences of AI traffic onto these networks. Right. So first on the Ethernet, right? So just another speed I put there. If you see the history, right, where we started, and this is really already in the kind of in the 70s, right, that we started, and I think most of us at some point in our education career, we've learned about Ethernet and how it started with Aloha, and then things like coax cables, CSMA CDs. It was for me kind of the protocols they learned at university as an example of, okay, how protocols are being built, how they evolve over time. But then the real first standardization of Ethernet was back in 1983. Right? So back then, I was not yet involved, but shortly after, I think my first networking training or networking course was probably end of the 80s. We started learning about the OSI model and so on, and Ethernet was, of course, already explained back then. And again, these protocols, kind of the way of working with collisions and so on, that was really the reason that we learned about Ethernet, to show the sophistication. Right? So 50 years ago, right? And since then, every so often a new speed, right? So we moved over time from 10 meg. So when I started being involved in Ethernet, it was 10 meg, it was coax. But then in the 90s, it went to fast Ethernet, and then gradually, every so often, the capacity went up. What is important to notice, though, is that it's more than just speed increases that we had over time. The Ethernet protocol itself has brought also kind of new ways of kind of new physics, new ways of building these networks. If I take switching, for instance, today is not based at all anymore on any collision, right? So where that was in the original implementations, all of that is still there, but it's not really used in current architectures, right? There is new use cases as well. And what is important is that also the ecosystem is growing, because Ethernet is being used in different flavors, so not only different speeds, but also different flavors in different industries. The ecosystem is ever growing as well, from cars to data centers and so on, of course, right? There is actually one constant in all of this. Focus has always been on interoperability, right? So yes, Ethernet has sometimes been abused to do some proprietary thing on top, or even at the physical layer. But in reality, all the successful deployments worldwide have had interoperability, right? So you can select different vendors being connected onto the same Ethernet, and that is still holding true today, right? So you buy your switch from vendor A, you have your NICs from another vendor, you have your router from a third vendor. All of these things, when they support the same standard, then they should be interoperable. Right? Now, latest status of Ethernet is 1.6, right? We'll see that in a minute. The standardization is being kind of finalized, right? So, but this year, you're going to see already 1.6 being deployed in networks. If you look at, well, I've seen some numbers from analysts on the selling of optical interfaces for 1.6 tera optical interfaces, and you see it already ramping up this year. End of last year, actually, we started. Right? Now, interesting to know that this is, again, not the end game, right? So 3.2 is already being defined right now. There is quite some pressure on the standardization organizations to do that as quickly as possible. There is really very big push to get to 3.2 as fast as possible, right? Which is a bit different in the old days, where the pressure came more from service providers, and it was all of us together who were building more, or were sending more traffic, or receiving more traffic, and as a consequence, these standards were kind of evolving. Now you see that these standards are often, the origins are often driven by hyperscalers who are planning to do more stuff even before we need this, right? So the ecosystem is there, it's much grower, but it has also changed a bit over time. Okay. What is the real driver for 1.6, right? So just following the speeds of the graph of the Ethernet Alliance is nice, but what is really driving the interest for 1.6 today is what is happening in data centers, and more specifically in AI data centers that now we call more often kind of factories, right? Data centers really focused on on AI, inference, but even more training, where we see that these data centers are really optimized for the one goal they have, right? And that is to build a system. And you could even see this as kind of a monumental distributed computing problem, right? So for doing AI, you need GPUs, and we are building our data centers in such a way that this is delivering, or this is giving you a computer system that is optimized for that task, for that big computer that is built out of GPUs, right? So we're really optimizing the data center for interconnection of these GPUs. And how do we do that? Well, what you see today in AI factories is that we split the network, or we do the split between what is front end, which is kind of talking to the rest of the network, and then the backend, where the goal of the backend is really to interconnect the GPUs in the best possible way so they can optimize their functioning. And so they become this one big computer, or they simulate being one big computer. What you see is a massive east-west traffic for this communication between the GPUs, right? So this is independent of what is coming from the rest of the network, right? So what is coming from your traditional DCI, what is coming from your customer connectivity, it's really traffic between the GPUs, where the GPUs together want to work, work on a common pool of memory they all bring in, and they work all together for this one goal, that they're being kind of a combined computer. Now, what we see in these networks today is that it's not the GPU that is the limiting factor. It is really the network. What is the best possible way to interconnect them? And there we see that speed is a major factor, right? The higher speed you can connect them, the better they can simulate being one big GPU instead of thousands or tens of thousands or even hundreds of thousands of GPUs together. To do that, there is different tiers typically in a backend network. So the terminology that is used there is scale up, means I have a number of GPUs that are in the same rack, and I will connect them in the best possible way. And I'm sure you've seen kind of NVIDIA announcements on the latest racks, where they don't really sell this anymore as like one GPU or one server with a GPU or a number of GPUs. They really sell this as a rack, and even more and more like multiples of racks, where all of the GPUs combined form this one major compute system. So scale up is within a rack. Of course, you are limited there in the rack itself, the physics of the rack. So next step is, of course, that these racks need to be interconnected with the backend network, and that is what we call scale out. Right? So we scale out these different servers to become like one big server. And then the next thing that is happening is something that is called scale across, where especially for high-end training, where you need to train a new model with hundreds of thousands of GPU, what we see in reality is that even a single data center might not be enough to host all of these GPUs. Not necessarily because of floor space, but often because of power. So what the hyperscalers want to do for the training of the models, they want to have multiple data centers working together to again form one big compute to get to in the best possible way to do their training, to train the model, right? So that is what is called scale across. So what is seen here is that the more capacity that you can use to interconnect these GPUs, the better this is going to work. And a consequence a bit of that is that the more GPUs you can connect to one switch, for instance, the better the model, the better this model works. right? So what is typically needed here is switches that have a lot of fan out. And how do you get fan out if you, at the same time, you want to optimize switches for footprint? You have like a 1RU, 2RU switch, whatever, and you want to optimize the number of ports that you can connect to it, is typically doing breakout on higher speed cages. Right? So if you have a 1.6 tera cage, a port that understands or can do 1.6 tera, typically what you're going to see in such a backend is that this will be broken out to be able to connect more GPUs to a single switch, right? So that is what is called this radix switching. So what we see there is 1.6 tera, not only for the speed, but at the same time, there is some modifications being done in Ethernet by the Ultra Ethernet Consortium to be able to make that model even work. All optimized for this GPU interconnecting problem. Major use case for 1.6. This is driving the whole industry in this space. This is driving the standardization, and the rest will follow later. Now, what is the rest? The rest is what we've seen before, that you upgrade your network because there is more traffic. What we see today is we have quite some customers connecting 800 gigi today. At some point, traffic in the whole network between the core routers is going to increase even more because there is more capacity being used, or more traffic overall from all of us. And then these interfaces will be upgraded to 1.6. Actually, I have already service providers today who are planning to go to 1.6 tera when this becomes available on core routers in the future. Right? So planning is happening. This is too early to do today on core routers, but this is coming in the future. This is combined as well with the shift we see in the architecture, where the service provider network, or the big enterprise network as an alternative, are more and more also looking into how to combine the IP and the optics world in a better way, right? The higher speed you go, the more benefit that you have from looking at these two worlds, these two layers at the same time. Better integration capabilities, better cost, less power. A lot of optimization can be done, and this becomes more valuable when you go to higher speeds. Right? So scale is increasing, things we've seen for the last, I would say, 30 years. I mentioned video, gaming, cloud, and of course now AI. What people really want to avoid is that you have to put too many links in parallel and then use kind of a lag in between nodes to be able to handle all the traffic at the same time. This is a model that works, of course. You can do, we've seen lags of 16 or 30 links in networks being deployed today. So 30 times 400 gig going to 20 times 800 gig. So that is deployed today. The challenge with lag is, of course, from an operational point of view, also from a load balancing point of view, is not always perfect, right? To spray traffic. Encrypted traffic or encrypted client traffic cannot necessarily flow, can only take one of the links. So you're very entropy dependent. So what we see there is that there is a benefit in combining multiple links and then go to the higher speed. And so this will happen in the networks in the coming years, but later than what is happening in the data center. I've put scale across here. I doubted a bit, should I put it together with the data center? I covered it there, what it means. But it's really like a data center interconnect type of problem. The difference is between data center interconnect and scale across is that the first one is normally going through your gateways, your data center gateways, and then it's kind of taking a similar path as the rest of the traffic, right? So you go out of the data center to other data centers or to other users, whilst the scale across is really optimized for this GPU interconnect problem, right? So that gives you other requirements, and typically the connectivity is a bit different. And that is where you will probably see the 1.6 tera coming first, right? Because remember in my data center, I had to go to 1.6 to have the best possible GPU to GPU interconnection. Now, if I'm forced to also go to another data center to have GPUs there and interconnect them, the requirements are not going to be very different, and I'm going to need the same type of interfaces there as well, right? And then you're going to see 1.6 over longer distances. How you solve it then from an optical point of view, there is different choices. You can, of course, it's going to be coherent, but it could be coherent directly through a plug in a switch or in a router. It could be a concept that we start seeing that is called thin transponder, where you put a coherent plug, but you put that in an optimized transponder, so that has a number of benefits. I mean, there is different choices from an implementation point of view. Okay, moving to standardization and the bigger ecosystem, right? So we said Ethernet needs to be interoperable or remain interoperable. So what's happening on the 1.6 side? So I've just put this for your reference. If you look at the 800 gig, it's a slide I think I made probably 4 or 5 years ago when 800 gig was the new thing, and where I tried to explain that the ecosystem, even on standardization, is a bit more complex than you would think. It's not just one standardization organization or standard organization that will define Ethernet completely these days. It's a combination of standards. IEEE is typically the one. There is also some organizations like OIF that have a role and are kind of standardizing or agreeing on some implementation or ways of implementing stuff that is kind of combined with IEEE. And then you have a bunch of MSAs, typically because the standard organizations take some time or too much time to get to a standard, right? So there is sometimes more pressure from the industry to get to a solution before the standard is ready. And so then typically you have an agreement between companies to work on kind of a common set of specifications to make sure they remain interoperable. So that was for 800 gig. Instead of going in the details of this one, let's move directly to 1.6. I'm sure you'll get the slides and you'll see that you can go back to 800 gig if that is of interest today. But if you look at 1.6, it looks a bit cleaner. Reason is that there is less of these MSAs. Some of these things that have been done in different projects, even in IEEE for 800 gig, have now been integrated from the beginning in the project. And the major project that you have to remember for 1.6 is IEEE 8023 DJ. That's the one that is deciding or defining the MAC and the PHY that is used on switches, that is going to use that is used on NICs, on routers, and so on. Right. So IEEE is defining kind of the MAC and the PHY layer. The second big component that you have is when you need to put interfaces into your router, your switch, of course, you need to agree on a form factor. How is my pluggable? How does my pluggable look like? Because of course, if the router or the switch comes with a certain type of cage, and I've decided to use another type of pluggable on the electrical side, they're not going to fit, right? Today, at this speed, you have kind of two players, two MSAs. On one side, QSFP-DD, that you might be very familiar with, especially if you're working in the wide area network. OSFP is an alternative that is actually much more pushed by the hyperscalers, and that will become much more visible on the higher speeds, and especially at 1.6. Where at 800, you have the choice today, or the first implementations you're going to see first on OSFP compared to QSFP-DD. I will handle that in a bit more details later on. And then the third, or the fourth actually, big player in the whole ecosystem is OIF, who's defining a number of electrical characteristics that is interesting, is defining coherent. They've done that for 400, 800, and they will also do that for 1600. So for 1.6 tera coherent plugs. And then they also define what is called CMIS CMIS and CCMIS, which is really the control channel that you have between a host and the plug to be able to agree on the number of parameters. The major thing, if you look in the slide from a technology point of view, is actually what you see here, this interface between the switch, the forwarding ASIC, or maybe the PHY that you might have on a system, and then the pluggable is moving to 224 gig SerDes. To get to 1.6, you need 8 of these. Right? So SerDes is really the lines that you have between your chips, between a chip and a pluggable, electrical lines today mostly, where the information is then put in on serial links to get in between these two modules or components, right? And then what you see, so that's on the electrical side within a system, right? So my system stops at the cage, of course. I put my pluggable in my cage, and then on the optical side, I have different flavors depending on the distance I want to cover. DR4, FR4, LR4, ZR. These are kind of an indication of the distance I can cover with these standards. Okay. So about the timing, I'm not sure if people heard that. I was still there. But so the expected timing for this is end of this year, right? So they are kind of finalizing kind of the details on the different layers of the standard. And let me move then to the kind of the next one that gives you an idea on what exactly are these people in IEEE defining, right? So this is the Ethernet organization, of course, but what they do in the 3DJ standard is looking at the MAC and the PHY and kind of standardize these things to go forward. And these are well, of course, not separate things, but it's really two different topics they need to cover. On one side, how are we doing kind of the MAC? How does it evolve? Because we move from 800 gig to 1.6, right? So this has to do with how do we do the framing, the addressing, flow control. Not too much of a difference there, but it needs to be defined, of course. What is a bit interesting now is, because we move to a higher speed, is the definition of the PHY. So how do we put a packet that comes from a NIC or comes from a switch or a router, how do we put that onto the line? But even before putting it on the line, how do we put it onto these links between the switch itself, the forwarding chip, and the pluggable, right? Because that is where all of this kind of physical modulation needs to happen, right? And so the PHY is typically, or IEEE is defining a PHY in kind of 3 layers: the PCS, the PMA, and the PMD. And you go more and more, of course, physical if you go down between the path of the PHY. But then you see what these things are defining, right? Of course, especially at these higher speeds, the fact becomes extremely important, right? Because there is a limitation on how long a signal can travel, even within a host, right? So people think sometimes about the PHY is important. So I want to do 10 kilometers, I want to do 50 kilometers, and so on. But even before you get there, the signal needs to be able to travel from your ASIC, your forwarding ASIC, your forwarding chip, towards the cage, and from there being understood by the pluggable, right? So that means FEC needs to happen there. There needs to be alignment. So how do I put my packet literally onto the traces between the cage and the forwarding chip? Right? So that is being defined at this higher layer is the PCS. The same at the PMA layer is really where we introduce now this 224 gig, right? So that means that the traces on my PCB, on my router, on my switch, on my NIC are now 200. So we call this 200 gig. In reality, it's a 224 gig signal, right? However, this is PAM4. So I tried to explain this on the right side. I guess many people might know this. So traditionally, you would do NRZ. So that means every change that you have in your signal means you move from 1 to 0. Now with PAM4, we try to reduce the baud rate. We try to reduce the number of these changes because that is very depending on the material you're using, and it becomes more and more complex to go to these higher baud rates. So what we do with PAM4 is we combine 2 bits into one signal change, right? So you can have, of course, 4 possibilities. Each of these 4 possibilities has kind of amplitude defined or voltage defined, and based on that, I can reduce my number of signal changes over time. If you look at 1.6, it was already the case with 800, it's all about PAM4. You will find PAM4 onto within the host itself. You will find PAM4 also onto the client optics. It's just to reduce the baud rate between 2 modules that have to talk to each other. Also, the layer where the SerDes links are kind of defined, although IEEE themselves are not defining SerDes themselves, but it is really where this is happening. So how is this traffic going over my lanes, my SerDes lines? And then you have the lower layer, really the physical medium dependent layer, where you will find the definitions of DR8, FR4, LR4. IEEE is defining the end-to-end requirements for these things, right? What they are not defining is the exact voltages that are used and so on. That is done by OIF. So that's a bit the complicated thing, right? So on one side, you have IEEE defining how it should work and so on, so the standard itself. But then, yeah, I have a slide in between, so let's first finish this one then. Then you'll see later that OIF is more defining the exact way of implementing it, so that 2 vendors who are following IEEE exactly know what type of voltage, what type of other choices they need to make sure that their equipment is interoperable with other vendors. And then the last line that I have on this slide is that once you go to 200 gig per lane, actually we had something similar with 100 gig, that opened up a new type of interfaces, not only at the highest speed, not only at 800 gig, but also at the lower rates. And why do we do this? Typically for power consumption. The higher rate you can run your SerDes lines, the more traffic you can put on one lambda, also on the optical side, the less power you're going to consume overall, right? So what you see typically is when they come with this newer standard like 1.6, it's also an opportunity to redefine some more PHYs at lower layers, like at 800 gig, 400 gig, and so on, right? Just as it is the same technology that they are using, is just less members in there. So that was more focused on my MAC5 for the ASIC itself, the switching ASIC. Next step, I told you QSFP, DD, OSFP. 2 choices that we as a vendor, we have to define when we build a router, when we build a switch, what are the cages we're going to put, because ultimately this needs to be compatible with the pluggables. What we see there is actually 2 different drivers, and that is the reason why you will find both into the market today. On one side, QSFP DD is what you typically see today in networks at 100 gig, 400 gig, and 800 gig, especially in service providers, is really focused on flexibility and continuity. What does that mean? We put a cage on a router, and that cage supports not only 800 gig, but it's backwards compatible with 400 gig, it's backwards compatible with 100 gig, even with 40 gig, right? So what we can do there is the pluggable decides what's going to happen, right? What is the speed that you're going to run your line on? Right? That is what QSFP DD is about, and it's giving you today. All of our systems on our wide area networking products today are using QSFP-DD. OSFP is a standard that is much more pushed by the hyperscalers. Hyperscalers typically don't care about backwards compatibility. When a hyperscaler upgrades its network, it's all or nothing. They're not going to mix different types of speeds onto the same box, except of course to go to kind of your uplinks. But they're not going to, they completely replace chassis. They work often with pizza boxes, but they do have also kind of full chassis. But they will kind of deploy full blocks of technology. So they don't really care about backwards compatibility. When they build like a 1.6 cluster, it doesn't need to interact onto the same system, at least with also kind of 800 gigs. So they might use different technologies because these are kind of implemented as blocks, right? And with OSFP, the characteristics, it was defined a bit later, characteristics are a bit different, but it allows you to actually go to higher speeds a bit more easily. So what you're going to see, and it's going to be new for most service providers, most of the non-hyperscaler networkers on the call, you're going to see at 1.6 much more, well, only OSFP in the beginning, because the technology to do it in QSFP-DD is not ready yet, right? So it will take more time. It's much more challenging to get to 1.6 tera with QSFP-DD than it is with OSFP. So you're going to see the first few years, everything that comes out on 1.6 is going to be OSFP. Different form factor for the plug. Seems very trivial, but of course very important. This has also an impact on how can I cool my system, because these MSAs are not only defining the pure form factor, but also the heat sinks and how you have to put the heat sinks, and so the whole ecosystem from a formatting, cage, and pluggable point of view. Then I said OIF, right? The OIF is actually doing different things that not everybody might be aware of, right? On one side, so they basically, it's not really a full standard organization. OIF is doing implementation agreements, meaning that vendors discuss between themselves how to make sure that what they are building based on IEEE mostly, how they are building interoperable systems. That is extremely important even on the electrical side, but then on top, OIF has done a number of things where they currently are a bit more known for is things like the 400ZR, 800ZR, and now 1600ZR coherent pluggable, right? So, but they do all of this, and on top also CMIS and CCMIS. So what you see here is from an electrical point of view, the most important thing for 1.6 tera is really this common electrical interface. This is defining how modules can talk to each other, right? So I have a pluggable with a DSP. I have my switching, or I have my PHY on my switch, on my ASIC. These things, of course, I have these SerDes lines in between, but we need to have an agreement on kind of voltages, I masks, loss budget. All of these things need to be agreed, and that is what OIF is doing, right? That's what you see with the signal integrity, right? So they work with kind of what IEEE has defined as kind of end goal, where what you need to reach, and then they define the specifics of getting there, right? Which is something that IEEE is not doing. However, it looks like two very different organizations. In reality, you will find that often the same people are in both, right? So they will define because they know the art of the possible because of their work with OIF, right? That's where they share and discuss with their colleagues from other vendors. They share what can be done, what the technology allows you to do. And then, of course, this needs to be put into a standard, and then they will build a standard that is able of doing that, right? And that is what IEEE is about, right? So they work kind of together to get to interoperable systems. Not only electrical, as I said, also coherent, and then CMIS. I don't have much more on the coherent side than CMIS because just of reason of time. But what you see here is I've put just a small copy paste out of one of these OIF documents, the common electrical interface. I've taken the one of 112 because the other one is still in draft version and it's a bit too early to share it, right? But it gives you an idea the type of things that need to be agreed for host and modules to be compliant and to be interoperable, right? It gives you that idea. And then another thing, just a side remark that I want to put here is that OIF is also the one that is defining Flex E. And if you can't wait for 1.6 ecosystem to be fully ready, meaning the standard is not there yet, the pluggables are not there, so how can I do 1.6? Actually, there is an intermediate step that that is available today that we call Flex E, where it is possible to combine multiple 400 gig interfaces. Right? You see here up to 400 gig interfaces can be combined with what is called kind of a shim, through a shim header into a Flex E 1.6 pipe. What you need to see here is, of course, these are my PHYs or just 400 gig, right? So no need for 802.3DJ there, right? It's all regular 400 gig. It's really at the chip, the forwarding chip layer that you can combine these four to behave to the rest of the system as a 1.6 tera interface, right? It's not 1.6 tera Ethernet, it's 1.6 tera bundle that you can build out of 4 parallel links. There is a number of consequences. I don't have the time to go into all of this. It's kind of an alternative of doing lags, advantages, disadvantages, but for the time being, this could be an option if you really need to transfer elephant flows over an optical network that is reduced, kind of reduced capacity. This is a way of getting there. Okay. And then what I want to kind of the last part that I have is to give you a bit of a feeling, okay, what can we expect first and when? So first of all, you need to have hosts that are supporting 1.6 tera. NICs, not today, right? So it's coming, right? But if you look at the industry today, all the fuss on 1.6 tera is about Ethernet switches, right? If you look at state of the art this year, what is available in the market from multiple vendors is a switch that supports in total 102.4 tera full duplex switching capacity. Right. This corresponds with 64 1.6 tera interfaces. Right? So if you see this box is a good example, you see 64 cages. Each of these cages can do 1.6 tera. However, what is more important today, even for like AI kind of backend fabrics or data center backend fabrics, is the breakout capabilities. I can split this 1.6 tera into 128 800 gig interfaces, or 256 400 gig, or 512 200 gig. So why is the 512 an important number? It's the number of 224 gig SerDes lines I have supported on my forwarding chip. Right? So it has 512 of these lines. So it can connect 512, it can do 512 connections. Let's call them NICs at 200 gig, which is this high radix thing that I was talking about, right? So because you want to reduce the number of hops the packet need to take, if you're happy with the throughput that you get at 200 gig, you can actually do much more spraying, much cleaner architecture, because you're breaking out all of these cages into low speed. So it's not 1.6 tera Ethernet, it is a 1.6 tera interface that is broken out into 200 gig, 400 gig, 800 gig, depending on the use case. Right? Now, this type of switches becoming available this year, what you're going to see is typically air-cooled versions and liquid-cooled. The one that you see in the picture is now air-cooled, but you're going to see liquid-cooled versions as well. 1.6 tera is kind of the flip over point where I can still do air-cooled, but then with liquid-cooled, maybe going forward that will become more and more a requirement. So liquid-cooled, because of the higher speed, you get more power consumption. Because of the more power consumption, you need to have better cooling or more cooling. And then at some point, air is not going to be helping you anymore, right? So you need to go to liquid cooled. Also, typically in combination with, especially in an AI data center, in what's happening on the server side, right? If, of course, these GPUs today, if you look at the bigger systems, they are all liquid cooled. If the whole rack is already liquid cooled, meaning the data center owner needs to have a liquid cooled infrastructure anyways, then it makes sense to also do liquid cooling onto its switches, right? To have a more consistent cooling infrastructure across the whole data center. So you're going to see that coming, and then a new technology that is going to become available as well, has been hyped for many years, is CPO. We're finally getting there. With CPO, very short, because I don't have a separate slide on that. The idea with CPO is actually that you try to avoid this SerDes line, this implemented in the PCB, right? So you have to imagine between my switch fabric, my switch itself, my chip, and my cage, I do this within the PCB, or maybe I do this with flyover cables to make this connection. The trend or the evolution is going to be at some point that we put this as an optical connection, right? So that actually the pluggable or the optical starts already together with my forwarding chip, and I don't have to cross a number of centimeters, decimeters to interconnect these two, right? So if you bring them much closer to each other, it brings a number of benefits, including power and cooling, of course, right? So first, this host, and then, of course, important as well is the transceiver side, right? So I need to have pluggables that are fitting there. There will be first generation this year. They will all be OSFP based, OSFP 224, right? Focus for this is in the hyperscalers on the scale out fabrics, right? So they want to use these transceivers for scale out, but then in combination with breakout. And then the flavors that you will see first is, or that you see already now available, is 2 times DR4 or 1 times DR8, right? So the 4 and the 8 is depending on the lambdas, right? So DR8 in this case, that's actually all 200 gig lambda. 2 times DR4 means you do 2 times 800 gig, and each of the 800 gigs is actually kind of a DR4 800 gig, DR4 compatible 800 gig. DR8 means it's 1.6 as implemented as 8 times T100, 200, not that different. FR4 longer distance, and of course multiplex. LR4 will take a bit longer to get there. In that context, I also mentioned things or terminology that you might have seen as 800 gig with LRO and LPO. The idea here is that a pluggable today, at this speed at least, needs to have a DSP. The DSP helps not only if it's a coherent pluggable to do the optical side, but also helps to do the signaling side over the SerDes, right? So it's a kind of a retimer. It is cleaning the signal when it comes from the chip. What you're seeing actually at 800 gig is this LPO and LRO, where some of these pluggables are trying to reduce on this DSP, only using a DSP in one direction, right? That's the LRO. I only use the DSP for TX, right? So what goes out, or even removing the DSP altogether. From a pluggable point of view, this is perfect, right? It makes the pluggable much more simple. It will consume much less power. The challenge is, of course, that the function that the DSP was doing is now gone. I cannot So that means the quality of my lines here must be much better, right? So that has an impact on the distance I can cover and so on. So there is a number of considerations, and the consequence is we don't know for sure yet if this will fully work also at 1.6, right? It's something you see at 800, might be there, you see possibly might be there at 1.6 or not. With that, I'm at the end of my presentation. Apologies again for the interrupt. What I try to prove is that 1.6 is maybe not fully there yet today. It's very imminent, right? Main driver, AI data centers, and specifically the backend. The rest is coming. Standardization is a bit of a puzzle, right? But it's there, right? And will be finalized towards the end of the year, right? And implementations are coming as well, right? Logical question would be, okay, you do an implementation, standard is not ready. Typically at this level, or we're now at the level or stability of the standards that if we need to change something, it's often well, a kind of a small microcode fix to be able to be fully compliant with the standard, right? So very minor changes. So with that, I'm done. The questions, Carl, is a bit challenging. I have more time, right? So if people want to stay a bit longer, if that works, I'm fine. I hope this was useful, and I'm done.
Thank you so much, Bruno. I love the concept of elephant flows. That's a fantastic phrase that I'm going to be using for myself from now on. And water cooling has come back. I remember water cooling from my mainframe days. So yeah, absolutely, it's great to see water cooling back into the world, coming into the world again. Does anybody have any questions? I know that we have gone over the hour, and I know that many people will probably have other meetings to go to. But does anyone have any questions that they'd like to jump in and ask Bruno whilst he's here? Oh, I think we're mainly getting, oh, we have in here with hyperscalers being the first to adopt 1.6T. What chance do you see for QSFP to become a viable solution at a later stage?
Yeah. But I think the second one first. I think I covered it, right? So it's still ongoing. So they didn't give up yet. So I think that's the good news. I'm not kind of entrenched in all of the latest, right? So but it's clear that the industry is focusing on one kind of OSFP also because kind of the ones with money or most money are behind it, right? And that is something I remember probably the first time I really saw that was when QSFP 28 became available. So probably 10 years ago, if not maybe a few years more. Question was, okay, why are we doing this, right? Why are we QSFP 28? Are we yet another or having yet another form factor? For me, that was the first time the hyperscalers decided, the data center decided what's going to happen on the optical level, right? And the problem is if the hyperscalers are not behind QSFP-DD, which they are not, right? So the question is, are the service providers or the combined service providers, and of course, technology-wise, it needs to be possible, but is that weight big enough to fully get the standard done, right? So of course, there is a lot of pressure, as I explained, for backwards compatibility. A service provider typically wants to have one line card where they can put multiple type of interfaces in there, multiple speeds, right? Is their arguments are going to be strong enough to get there? I don't know. If I look at even on form factors like CFP4, for instance, that disappeared completely. Why? Because there is no drive from the hyperscalers. And if you're a pluggable vendor, of course, you're going to focus on where most money is, and most money is with the data centers. Right.
Indeed, and of course, the hyperscalers aren't just data center builders. They build their own networks between the data centers, so they are going to be driving not only the local and the metro, but the wide area as well.
Indeed, and because they kind of standardized on OSFP in the data center, you see also what they ask us for, even for their wide area network, is also OSFP, right? So they are not all the same, by the way. So I cannot mention who does what exactly, but we have a hyperscaler customer, or at least in talks with one, where only kind of our systems we have different types of kind of switching architectures, but the one that is based on Broadcom is a given, right? They will not choose anything else. Whilst another one will say, okay, but I still see the benefits of having kind of a customized forwarding chip, and they still will go for FP systems. But even that choice has an impact on what type of pluggables will become available in the future, right? Because if that hyperscaler goes for FP, as a consequence, today all our systems are based on QSFP, so they will have to standardize on QSFP. You see, there is a big ecosystem, but of course everybody is looking from his own perspective. And if your wallet is bigger than the rest of the world, then of course you have more influence.
Yeah, the phrase "he who pays the piper calls the tune" is comes out here.
Indeed.
Fantastic. Okay, I think that probably covers most of the things for today. What I will do is obviously when I take the recording, I'll trim out the little bit where you disappeared off there, Bruno. So don't worry about that, and I'll be able to share that to all of the attendees. So thank you very much. And also, Bruno, if you could send me your slides, that'd be also useful. I'll be able to set up a downloadable link for those, if that's okay with you. And also, there'll be the contact details on there so people can ask you questions directly, or of course speak to your Nokia account managers, everybody. So yes,
that's always a good idea, Carl. Always.
Absolutely. I thought I'd get that one in for you, just
Thanks a lot. Very good idea.
to make sure that everyone gets the right call to action. So, but thank you so much for your time, Bruno. Really interesting. It went over my head a lot, I must confess, being a marketing bear of little brain in terms of the networking. But thank you so much. And thank you all for attending. Thank you all for your time. And I will be sending out the links later once I've got it all edited down. So thank you all. Thank you. Goodbye.
Bye all. Thank you very much.
Okay. Thanks, Bruno. That was really appreciated. Yeah, like I say, a lot of it went way over my head. My networking days are way past me.
No problem. I mean, everybody has his focus, right? And have to do